Welcome, this is Coach Dorf. Today we're going to begin section 2.7 that talks about derivatives and rate of change. Now, before we get into that, I want to review a problem from last time. Last time we were looking at the limits at infinity and horizontal asymptotes. So suppose I have this problem from last time. We talked about an example at the end of class or the end of the video that was similar to this. But I want to do this again, and I want to extend this also to the fact if we look at the limit as x goes to negative infinity. So from last time, if we look at this one, what we want to do is we want to look at and ask ourselves, what is the degree of the numerator and what is the degree of the denominator? In the denominator, the degree is 1, right? Because the largest exponent on x is 1 there. I circled that in red. There's not a 1 listed there, but when it's just x, that means x to the first. What's the degree in the numerator? Well, we can't tell because it's a square root. We can't say it exactly, but in the top, it acts like the square root of x squared, which is like an x to the first power there. So the top acts like a degree 1 and the bottom is a degree 1. And so by the result we had from last time, the limit should be the square root of 9 over 2, which is the same as 3/2. But we need to actually prove that or show that that's the case. To show that, we do the following. We look at the limit as x goes to infinity, and I'm going to multiply the top and bottom by 1 over x. Again, I have to have the same thing I multiply the top and the bottom by. They have to be the same. And I want to do 1 over x because I want to do 1 over x to the degree of what's on the top and the bottom. And the top acts like degree 1, the bottom is degree 1, so we do 1 over x to the first or 1 over x. Now, I have some difficulties trying to bring this 1 over x into the square root. So we're going to rewrite that as a term under a square root. So let me rewrite my function here. And on the top, I'm going to rewrite 1 over x as the square root of 1 over x squared. And I'm going to keep the bottom as it is. So what we're noting here is that 1 over x is the same thing as 1 over x squared if x is a positive number. It's greater than 0. And I know it's going to be greater than 0 because x is going to infinity. That means x has to be a positive number because I can't go to infinity from a negative number. I have to be having positive numbers here. So now I can go ahead and bring in those terms. I can multiply them in. On the top, when I do that, I'm going to have here, when I multiply the 1 over x squared under the square root by 1, I'm going to get 1 over x squared. And when I'm going to multiply by 9, I get 9x squared over x squared. So that's under the square root. And in the denominator, when I bring that in, I use a different color here, I'm going to get 2x over x minus 4 over x. So now when I simplify that, again I have 1 over x squared plus 9 under the square root in the top. In the bottom I have 2 minus 4 over x. And then using the result number 1 from last time, 1 over x squared goes to 0. 4 over x in the denominator goes to 0, and so I end up with a 0 plus 9 under the square root, and on the top I have 2 minus 0. So that becomes the square root of 9 over 2, which is the same as 3/2, which is what we thought we should get. Now let's do another example, and this time let's look at it instead of x going to infinity, we're going to have x go to negative infinity. In all the examples we've seen so far, when x goes to infinity, that limit gives us the same result as x goes to negative infinity. But it's not going to happen this time. So when we do this one, I do the same thing. I say the degree on the top acts like 1 and the degree on the bottom is 1. Because of that, I'm going to look at multiplying the top here by 1 over x and the bottom by 1 over x. And that's because degree equals 1 or acts like 1. Now, what happens when I do that square root? I want to bring in that 1 over x in the numerator under the square root, and this is where it gets a little bit tricky. 1 over x equaled the square root of 1 over x squared if x was greater than 0. but 1 over x equals the negative of 1 over x squared if x is less than 0. This is a tricky part here. If x is less than 0, so we're looking at the green case here, if x is less than 0, 1 over x is a negative number, right? So let's take a number that's x is less than 0. Let's take negative 2. What is 1 over negative 2? It's a negative number. Now, if I do the square root of 1 over x squared, so put in negative 2, so let's do this. So for example, let's just say x equals negative 2. Then 1 over negative 2 is a negative number. But if I look at 1 over negative 2 squared, and I take the square root of that, that's 1 over 4 under the square root, which is 1/2. That's not a negative number. So we have to do negative 1 over the negative 2 squared, and that would give us 1 over negative of the square root of 1 over 4, which is negative 1/2. And now these two are equal. So if x is less than 0, or in other words, it's a negative number, then we have to use 1 over x equals negative of the square root of 1 over x squared. So going back to our original problem, remember we had the limit as x was going to negative infinity, and we had on the top 1 square root of 1 plus 9x squared, and in the bottom we had 2 minus x. And we were multiplying the bottom by 1 over x. We need to multiply the top by a negative 1 square root of 1 over x squared. So when we do that and we bring those numbers in here, we're going to get a negative square root of 1 over x squared plus 9x squared over x squared in the numerator. And in the bottom we have 2x over x minus 4 over x. If we simplify that, we have a limit as x goes to negative infinity of negative 1 over x squared plus 9 over 2 minus 4 over x. And using that result, number 1 from last time, the 1 over x squared in the numerator goes to 0, the 4 over x in the denominator goes to 0, and so we end up with the negative square root of 0 plus 9 over 2 minus 0, which is negative square root of 9 over 2, which is negative 3/2. Notice we get different answer than when x goes to negative infinity as when we get x goes to positive infinity. So in summary here, the limit as x goes to positive infinity of the square root of 1 plus 9x squared over 2 equals 2x minus 4 equals 3/2. But the limit as x goes to negative infinity of 1 plus 9x squared over 2x minus 4 equals negative 3/2. And if you go on to Desmos and you sketch the graph of this, it's going to look something like this. Let me put some points in here. I notice there's a vertical asymptote at x equals 2. And that's because we have this denominator. This means there's a horizontal asymptote at y equals 3/2. And that's going to be on this side here, on the positive side. So this is y equals 3/2. And then on the negative side here, we get a horizontal asymptote at y equals negative 3/2. So that's going to be on this side over here. And so my graph in purple, if you go on Desmos, is going to look something like this. There's that vertical asymptote. It's going to bump up here and go down like this. All right. So when you have these square roots, these functions with the square roots, and you're doing the limits, you don't always get the same answer as x goes to infinity as you do as x goes to negative infinity. All right, so that was a review from last time. So now we're going to talk about section 2.7, and that's about derivatives. What's the setting here? Again, what we want to do here is we have some graph of a function. In this case, we're looking at this, and we want to find what is I have a point here, and I want to find this slope of this tangent line, and that's where calculus and derivatives come in. Now, this tangent line, again, is not the trig tangent line. When we say tangent line in this case, it means that it only intersects the red graph once, and that's at this point right here, that blue point I just colored in there. It only intersects the red curve once there. The difficulty here is to find the slope of a line. To find the slope, you need 2 points. You need, in this case, y2 minus y1 over x2 minus x1. That's what the slope of a line is. The rise over the run. That's another way you can think about it. This is the beauty of calculus, that we're able to do this, to find that slope of that line. So let me review a few things here. So before calculus, suppose the slope of some line is 2/3, and you have the point, we'll say negative 3/4 is on the line. Then the equation of that line is where you're going to use y minus y naught equals the slope times x minus x naught. So here we've got x naught is negative 3, y naught is 4, and those come from here. That's where that 3 is, and the 4 is right here. What about the slope? The slope is m, and that is 2/3. And that comes from here. So now I'm going to substitute these into my equation here. Y minus y naught equals m times x minus x naught. So I'm going to get y minus 4 equals 2/3 x minus a negative 3. So I get y minus 4 equals 2/3 x plus 3. Simplifying it on the right, I multiply the 2/3 by both terms here, and I get 2/3 x. 2/3 times 3 is going to give me a 2. And then when I subtract 4 from both sides, I get 2/3 x plus 6. And that's my equation. Some of you probably learned a different way to do this, and you could write this in the following way. You could use y equals mx plus b formula. So we know here that we have the 2 points x, y, we were told was negative 3, 4, and we know the slope was 2/3 in this example. Okay, and you want to find b. So you do y equals 2/3 x plus b, and then you substitute in the 3 in here for x, and you substitute in the 4 here for y, so that you get 4 equals 2/3 times the negative 3 plus b. So you get 4. 2/3 times negative 3 will be negative 2 plus b. Add 2 to both sides, and you get 6 equals b. So you have y equals mx plus b, and we know that, again, m equals 2/3. That came from up here. And b equals 6, and that came from up here. So you end up with y equals 2/3 x plus 6. And that's the same thing as what we got up above. So either way works in doing that. Now, that was pre-calculus. That's not calculus yet, because you're given the slope. What you're going to happen in calculus is you're not going to be given the slope. So how do you figure this out? Well, let's look at this example here. Suppose I have my function f of x equals x squared minus 3x plus 2. What does the graph of that look like? It is a parabola. It looks like a U shape. If I draw some points in here, the graph of that is going to look like something like this. There's the graph of that here. And suppose I want to find the tangent here at this point, x equals 1. So what is the slope of this tangent line at the point 1, 0? All right. We know what the point is. We have this x naught is 1, y naught is 0. And there's that 1, and that 0 comes from here. But what we don't know is what is m. That's where calculus is going to come in, because we don't have more than one point here on the purple line. We just have that one point at 1, 0. All right, so how do we figure that out? Well, what you're going to do, if, again, I look at my curve here in red, it looks something like this. We're going to take the point 1, 0 that we had, and we're going to take another point on the red curve. Another point is 3, 2. That's part of the curve that's part of the parabola there, and I could find the slope of this. What is the slope there? The slope is y2 minus y1 over x2 minus x1. So in this case, I'm going to do 2 minus 0 over 3 minus 1, and that'll give me 2/3. Just to make sure we're all on the same page, that 2 comes from there, the 0 goes there, and in the denominator, I've got the 3 for the x value here, and the 1 comes in there. So that's how I find the slope for there. Is that slope, that blue line, similar to the slope of the purple line we're trying to find? Well, not really. No. So what we can do is we'll look at this again, and we'll take another example. Let's take 2 more points. Again, we've got this blue point 1, 0. We just took the point 3, 0, but let's get a point closer to that blue point. Let's take this point here. That's a point still on the red line. That point is 2, 0. Its slope is the differences of the y's, so 0 minus 0 over the differences of the x's, 2 minus 1, and that's going to give me 0. So the slope of this line here is 0, and that makes sense. It's a horizontal line. That's why it has slope 0. What we're doing here is we're trying to get points on the red closer and closer to it, and that then becomes, we have to do the idea of the limit. Let me just mention here that these 2 examples we did, we found this slope here is also known as the average rate of change. So if you see a problem that says find the average rate of change over some interval, then you're going to do this type of approach. You're finding the slope of it over those 2 points. You're given 2 points for the average. What's neat about calculus is you're finding the instantaneous rate of change, or the slope. You're finding the instantaneous rate of change, which is different here. So now, as we get this blue point closer and closer to the point 1, 0 that we want, so as the second blue point on the red parabola gets closer to the blue point 1, 0, we are using the idea of limits. In essence, what we're doing is we're doing the limit as x2 approaches x1. That's kind of the idea we have here. And applying that to the slope, so the slope of the tangent line, the one that we were trying to find in the original problem, is the limit as x2 approaches x1 of f of x2 minus f of x1 over x2 minus x1. Here is my point x1, y1, and I'm trying to get a point here. We'll call that there, and we'll call this point here x2, y2. Now notice that y1 is the same thing as f of x1, and y2 is the same as f of x2. So when I plug these in to the slope formula, that's why I have f of x2 minus f of x1. All right. In general, then, we write the following. In general, we say the slope equals the limit as x goes to a of f of x minus f of a over x minus a. And we can also do this if we substitute, or if we substitute x equal a plus h, we get that the slope is the limit as h goes to 0 of f of a plus a minus f of a over h. And this is what's commonly known as the derivative. This is where we get the idea of the derivative from, and this is the definition of it. So just to make this formal here, and this is a big deal here. So it may not seem like a big deal to you, but this is a really important, this is one of the most fundamental main ideas of calculus. So if you take a moment here, well, let me first write this down. So the derivative of a function at a number a is given, we write that as f prime of a equals the limit as h goes to 0 of f of a plus a minus f of a all over h. Or we can also write it f prime of a equals the limit as x goes to a of f of x minus f of a over x minus a. All right? Now, this is a big deal. This is, if this were an art class, this would be like the Mona Lisa of art. If this was a music class, it might be like the Beethoven's Ninth Symphony. If this were a literature class, this might be like Shakespeare. If this were a soccer class, this would be the best soccer player. Maybe I'm really old, but my age was maybe Pele or Messi now, Serena Williams for tennis. This is a big point. This is the fundamental idea of calculus, that you can find the derivative, or that the derivative is the slope of this tangent line, and you can do it by only having 1 point on the curve. You don't need 2 points like you need it in geometry. Really big idea here. As you're watching this, I think what you should do is clap. So here's a moment. Let's just say I just introduced this to you. I want you to take a moment, and I want the whole class to clap. I'm acting like I'm hearing the clapping now, so great. Thank you for clapping there, because this is really an important idea. Let me do an example to show you how you would use this idea. So find the derivative. Here's a problem. Find the derivative of f of x equaling x squared minus 3x plus 2 at the point 1, 0. So what do I do here? I'm going to use, let me switch my little thing on my pencil here, my Apple Pencil. So I'm going to use the definition. What is my point A? So what is A? A is 1. That comes from the fact that x is 1 here. And I'm just using this idea here, substituting it in there. So now we have the limit as h goes to 0. Now what is f of 1? So I'm going to do f of 1. Let's see, we'll just write this in a different color. So what is f of 1 plus h? Well, here's my f in red. So I'm going to put 1 plus h in there. So I'm going to get 1 plus h squared minus 3 times 1 plus h plus 2. And when I do that, I'm going to get 1 plus h squared is 1 plus 2h plus h squared. And this is why we reviewed this the first couple weeks of classes. How do you figure out that 1 plus h quantity squared? You'd have to do 1 plus h times 1 plus h, and you get what I just wrote down. Also then, I've got minus 3 times 1 plus h. We also reviewed this. You have to distribute that 3 into both terms there, so I'm going to get minus 3 minus 3h. Don't put plus 3h, it has to be minus 3h plus 2. So this is what that is, what f of 1 plus h is. What's f of 1? Well, I put that back in, I'm going to get 1 squared minus 3 times 1 plus 2. So that's going to be 1 minus 3 plus 2, and that is going to equal 0. So going back here, I've got the limit as h goes to 0. I'm going to put in this 1 plus a, f of 1 plus a, which is going to be 1 plus 2h plus h squared minus 3h, sorry, typo there, minus 3 minus 3h plus 2, and then I've got minus 0, and that comes from this part here, the f of 1 all over 8. Now let's simplify this. I've got in green here, I've got 1 minus 3 plus 2. That all equals 0. So that's going to cancel out. Let me put that. Those cancel out to be 0. And in purple, I've got plus 2h minus 3h. So I'm going to get in purple minus h. And then I've got that plus h squared here. That's going to go down there. All over h. That's from the bottom. So now I simplify this. Now, if I do the limit, like we've done before, if I do the limit, I said do the substitution method, I get 0 over 0. So what did we learn when we got that? Well, we needed to factor something out so that we could cancel what was on the top and what was on the bottom. So in the top, I'm going to factor out an h. That's going to give me a minus 1 plus h on the top. And on the bottom, I have an h. Now I can cancel out this h with that h. And remember, when we talked about limits, this is like saying, I knew that I should have, because I got 0 over 0, I knew I should have had an h minus 0 or an h that cancels on the top and the bottom, and I just got that. So then I just have the limit as h goes to 0 of negative 1 plus h, and that equals negative 1. This tells me this is the slope of my curve. And again, what was my curve that I had? Well, it looked something like this. And we were looking at the point here, 1, 0, and we were looking at the slope of that tangent line right there, and that slope is negative 1. That's what we just figured out. That's really cool. This is really neat in calculus. We get that we can able to figure out that slope of that line with only one point on that purple line. That's the idea of calculus. All right, now let's do another example here, something that you might see in your homework. All right, so there's a difference between average velocity and what we'll call instantaneous velocity or just velocity. So we have a difference here. Average velocity, we're going to be using 2 points, and we're just trying to average out the results there. Instantaneous velocity is what we just did with calculus. That's where we only have 1 point, and we're figuring this out. So be careful to notice if you're doing your homework and it says average velocity, you're doing one thing, and if you're doing instantaneous velocity, you're doing something different. So let's give an example that shows how both of these are computed. All right, so let's say we have a particle here is moving on a straight line. So let's see, and that's given, the displacement is given by the function s equals 1 over t, where t is measured in seconds. So part A, find the average velocity over the interval from 1 to 2. And part 2, we're going to find the instantaneous velocity when t equals 2. So let's look at these. So for the first one, so part A, the average velocity on 1, 2 is going to equal the differences of the y's or the differences of the x's. In this case, that's going to be f of 2 minus f of 1 over 2 minus 1. So I'm going to, where f of t equals 1 over t. So we get the average velocity equals f of 2 minus f of 1 over 2 minus 1. That's going to equal 1/2 minus 1 over 2 minus 1. And if I simplify that, I'm going to get negative 1/2 over 1, or negative 1/2. What about the instantaneous velocity? So instantaneous velocity is using, I have to use that definition at t equals 2. So I'm going to be looking at f prime of 2, and that's going to equal the limit at t goes to 2 of f of t minus f of 2 over t minus 2. So notice here, we are using the second definition of derivative, right? So there was the first one, which was the limit as h goes to 0 of f of a plus h minus f of a over h. The second one was the limit as x goes to a of f of x minus f of a over x minus a. We are using this one this time. In the previous example, we used the first definition. So I want to show you both so you are aware of how to use both of them. So I've got f of 2 equals the limit as t goes to 2 of f of t minus f of 2 all over t minus 2. And just in case anybody's wondering, it doesn't matter if I have an x in that, like that circle part, I have x going to a here, and I have x's, but in this one that I'm doing right now, I've got t. It doesn't matter, it's the same, it doesn't matter what letter it is, it works out the same way. All right, so what is, recall here that f of t equals 1 over t. So we're going to put these in here. So we have the limit as t goes to 1/2 of 1 over t minus 1/2 over t minus 2. So now this is similar to the types of problems that we were dealing with when way back in section 2.3 when you were trying to compute limits. How do I compute this limit? Well, you could put the 2 in, substitute it in the numerator, then you get 1/2 minus 1/2, which is 0. And in the denominator, you get 2 minus 2, which is 0. So you have 0 over 0. So that means you have to manipulate this some way so that you can cancel out a t minus 2 on the top and a t minus 2 on the bottom. We know it's going to be a t minus 2 because we have this t approaching 2 there. All right. So how do I manipulate that to get that t minus 2? Well, I'm going to take what's in the top here in the numerator, and I'm going to combine that to get one fraction. So I get a common denominator. My common denominator will be 2t. So I'm going to have a 2 over 2t minus a t over 2t. That's what's going to be in the numerator. And in the bottom, I'm going to have t minus 2. So I've rewritten this, what's in the top, to be that. Now, I'm going to go ahead and simplify what's in the top. Maybe by making one fraction, I'm going to have 2 minus t over 2t. And in the bottom, I have t minus 2. So I have a fraction over a number, which I can write as a fraction by putting a 1 in there. So that's equivalent to saying I've got a fraction divided by a fraction. So I can simplify that as taking that top fraction, 2 minus t over 2t, and multiplying by the reciprocal, which is t minus 2. And then we remember that this 2 minus t, if I take out a negative 1, or if I multiply everything by negative 1, that's equal to negative t minus 2. So what I have here is I have the limit as t goes to 2 of negative t minus 2 times 1 over 2t times t minus 2. Now I've got the same thing on the top and the bottom. I can cancel those out, and I get the limit as t goes to 2 of negative 1 over 2t. And when I put the substitute now in for the t equaling 2, I get negative 1 over 2 times 2, which is negative 1/4. And that's what my limit is. All right. So let's look at this. What does this mean graphically? What's my function was f of t equals 1 over t. That is, of course, this Kung Fu Panda function I mentioned earlier. All right, or the hyperbola is what its official math name is, if you want to be picky on that. And here is the point where t equals 2, and this point on this curve here then is going to be 2 comma 1/2. And we're trying to figure out what is the slope of this line here. Slope, and that's going to equal the derivative at 2, which we just saw was negative 1/4. And that makes sense. That looks like it's a negative 1/4. It's definitely negative because it's going down, and it's less than the slope of negative 1. So meaning that it's, sorry, I shouldn't say less than negative 1, but it's the slope on there is getting closer to a horizontal line, so it's between negative 1 and 0. And so negative 1/4 makes sense with that aspect there. All right, I think that's good enough for today. Hope this helps you. Have a good day.